So with the graphs, I emphasized yesterday, there's Christian. I emphasized yesterday that your graph needs to have a meaningful title, right? Not acceleration versus mass, right? Anyone could read acceleration, which is spelled something like that. Acceleration with the units and WM for washer masses. Anyone could read that you have hanging mass and acceleration as the axes. Putting that as the title of the graph would just be a waste of everyone's time. Your title should tell you what is on there. Then you put your data points on there. So you have data points like and then you make your best fit. The reason I have you do it on paper rather than on the computer is because on the computer, well, it does a routine, what we call the least squares fit, where it calculates the distance from the closest distance from the line to each point and then adjusts the line to minimize. It's actually the square of those distances, which is why it's called least squares. But what I want you to do is to use your ruler in your brain to find the line that is the closest approximate facsimile to that data. So you want to make sure that when you draw your line, you have the distances above and below are just about equaled out. Typically, that line doesn't go through any of your data points. Now, I say typically. Sometimes it does. But many times it doesn't go through any of your data points. But that's your best fit line to all of your data. So that's taking all of your data into account, not individual points. Then when you find the slope, you need to find points that are actually on the line as far apart as you can get. Points that are easy to read, they're as far apart as can get. Because your plotted points rarely fall on your line, you will lose points on your grade if you use the measured data points to find the slope. Because you're trying to find the slope of the line. If you use your measured data points, you are simply throwing away all of the data except for these 2 points. Well, that's not what we want to do. We want to take the representation of all of the data. So even if it so happens that one of your data points falls in your line, don't use it for finding the slope. You'll still lose points. Okay, Leslie, you had a question?
So then how do you do it?
You choose 2 points that are as far apart as possible on the line that you can identify what the vertical and horizontal positions are. So you use graph paper that has all these tiny little lines, and if you find a place where the line crosses 2 of those, then you can determine exactly what that point is. Well, exactly, much more accurately.
You still lose points if you don't use far apart points, but you still use points on the line, but not the farthest.
You want them as far apart as you can. That's kind of a judgment call. But you want them far apart. If you choose 2 points that are like one's here and, okay, let's turn that function off. One's here and one's here. Your accuracy of that slope is much worse because your uncertainty for each one divided by the rise and run is a much bigger percentage. And so it gives you a much bigger error if you choose closest points. If you choose farther points, you have a much smaller error in your slope for the same exact line. Now, something I didn't say that I should have said at the beginning. At this point, some students simply don't know how to make a graph. And so need to make some things clear. You need to have consistent spacing down here. Sometimes people put like the distance between point 1 and point 2 is twice the distance between point 2 and point 3. Well, that's not going to work. It needs to be a linear, consistent spacing. And of course, it goes without saying that you need to very carefully locate where the points are and then drawing the line. I just said you use your ruler and draw a straight line. I did say use a ruler, right? Yes, because you don't freehand. If it looks like my line, well, that's going to cost you points too, because you can't find the slope of my line. It's not straight. So you use a ruler to draw a straight line. Some people think that making a graph is a connect the dot game. It's not, right? You're not connecting the dots. Some people think you take the top one and connect it to the origin. It's not. That would be throwing away all but one of your data points if you just took the top one and connected it to the origin. Right? You're finding the best approximate fit to all of the data. So the reason that you had to do that full page graph by hand was to work on these skills of making a graph. And if you have any questions, please come and ask me. Now, of course, the labs are due tomorrow. I plan on, since I'm not going to be teaching next week, to make sure I get all of the labs graded in the evenings. Well, except for Sunday evening. We're arriving in Washington, D.C. about an hour before kickoff between the Raiders and the Washington Redskins there in Washington. I won't be at the game, but pretty sure it'll be on local TV. So any questions about the graph? Erica.
So when you were talking about the two furthest points, so you want points that are closer than together to be making a measurement?
You want to find the slope from points as far on the left end and as far on the right end of the line as you can find that are easy to measure. Right, like I said, it's a judgment call. Any other questions on the graph? Did lab yesterday go well? For a few people. Did lab yesterday go poorly? Okay. Are you non-committal? Yes. Okay. So let's get into this. How to solve problems with circular motion. Start as you would for any force problem. So for any force problem, you draw a diagram of what's going on, and then you add the forces so you have your free body diagram. If it's a force problem, you just start with that. Then choose your axes. And we talked about how you choose your orientation. And in the problems I'm going to run right now, we'll have to talk about how do we choose our axes each time. Then you find the radial component of each force, break them into components. I only talked about the radial here. And apply Newton's second law. The sum of the forces in the radial direction, we usually put sum of the forces in the centripetal direction, sum of F sub C. Here I put sum of F sub R, same difference, is equal to the mass times the acceleration in that radial direction, which once again, we usually put A sub C. And then we solve it. And remember, if it's going in a circle, the acceleration toward the center of the circle must be the centripetal acceleration of V squared over R. So let's go straight to a problem. And actually, Michaela wanted me to look at what? Can you describe it for me? I understand waiting for the computer to load.
Part C of 3, the takeoff of a commercial jet has a speed of 64 meters per second and the tires have a diameter of 0.82 meters. And this is what is the force unlimited by 0.85 times negative 15 kilograms bacterial things per pressure. Sorry, I did that really fast.
Okay, it was a mass. Is that what they gave you?
Yeah, no, they gave us the speed and the diameter.
But of the something bacterium.
Yeah, they gave
Oh,
you
yeah,
the
they gave you 0.85 times 10 to the negative 15 kilograms. That came
Okay, 0.85 times 10 to the minus 15 kilograms?
Yeah.
Okay, so we have our problem here is a wheel that's spinning. And compared to the ground, the velocity of the center of mass is equal to 64 meters per second. That's their center of rotation, I should say. The velocity of the center of rotation is 64 meters per second. What's the speed of the ground? The ground is stationary, right? So the first thing I'm going to do is say, okay, the bottom of the tire is stationary. The center of the tire is moving at 64 meters per second. If I switch my reference frame to talk about how fast the bottom of the tire is moving with respect to the center of the wheel, how is that going to change things? If I say the center of the wheel is stationary, what's the ground doing? It's moving. It's moving in the opposite direction the airplane is at what speed? That same 64. So if I change to, so this was the Earth reference frame here. And now I'm going to switch to the airplane reference frame. So this is stationary, and we have the Earth that's traveling underneath in the opposite direction. Now, why did I do that? Right? I do something in a problem. Frankly, I've done so many problems, I kind of know where to go. But you guys haven't done literally millions of physics. Well, okay, literally millions, probably not. Thousands of physics problems in your lifetime. And so you don't have that feel for how a problem goes. So how did I know to do that? Well, going to the end of the problem, it asks with what force does that bacterium need to be held to stay on the wheel? And so my brain went through the process of saying, okay, what would make that bacterium not stay on the wheel? And it would be its inertia. If the wheel is rotating, its inertia, it wants to keep going in a straight line. But to go in a circle, I need a centripetal acceleration toward the center that I know is v squared over r. And so if I have an acceleration v squared over r, then I know Newton's second law says the sum of the forces toward the center has to be mass times acceleration. And so because my acceleration was dependent on v for the surface of the tire rotating, I wanted to find v for the surface of the tire. So I went through all of that thought process before I got started. So my concept, really, if I was going to write this like I do on a test, my concept would be bacterium's inertia makes it, quote, want to. I put quote because, of course, it's not really anthropomorphizing if it's a bacterium because it has life, but you know what I mean. Makes it want to go straight because inertia is certainly not life. So need a force to accelerate it into a circular path. Find speed of edge of tire so I can find centripetal acceleration and then use Newton's second law. That's my concept here. All of that thought went through my mind before I got started. I got started on the problem because, of course, what's the first thing we do? We just want to get going. Then I remembered, I'm teaching. I've got to go through, this is why we do things, so you have a better understanding. So we have now determined the speed of the edge. So we have, find the speed of the edge, so we can put it into this equation. So we have the centripetal acceleration is v squared over r is equal to 64. Well, I'm not going to put it in yet. And then I have on the tire, here's my bacterium. My acceleration toward the center is like that. Sum of the forces toward the center is equal to, what's the only force toward the center? I don't care. It just says with what forces it have to be held. So I'm just going to try to find whatever the force is toward the center. I'll put FS for force sticky. And so then I put in my numbers. 0.8, was it 85? Yeah. Times 10 to the minus 15 kilograms.
What's the 0.85?
That was the mass of the bacterium for her problem. Because you're probably going to have a different number for yourself. And then my speed is 64 meters per second, quantity squared, divided by the radius, gave me the diameter here is 0.82, so the radius is 0.82 over 2, or 0.41. And then I put it in the calculator and I get my answer. Now keep in mind that 64 meters per second was the same number as this V here, but I had to establish what the speed of the surface of the tire was with respect to the center, not just take the speed of the airplane. So numerically it came out the same. You have to be careful. You could have a problem where that's not the case. So there's an example of working a problem with rotation. Now the actual work of this problem was real trivial, right? This work right here was not hard. It was the physics, which is this part here, that is non-trivial. That's what we're looking for in a physics class, is developing that thought process, being able to look at the situation and determine what's going on. And then it's assumed that your math skills will allow you to do the rest. So, any questions about that problem? Then let's look at another problem. A roller coaster. This is a different problem than the one I started last class period because, well, the very last one today, which I'm sure we won't get to, is the one I started with last class period. A roller coaster includes a vertical circular loop. So it's a circle. Remember the one we started last class period, it had a smaller radius at the top so that it can go slower. What's the minimum speed at which the car must move at the top of the loop so it doesn't lose contact with the track? So when it's at the top of the loop, it's specified. So I need to start my problem. What was the first step I said in solving your problems? First, draw a figure and a Freebody diagram. So it's actually drawn for us. They drew the Freebody diagram both at the top and bottom here. Well, because there was a second part to the question about the bottom. So here we have the Freebody, well, the forces at the top. And we could draw it as the technical Freebody diagram just by having, the two forces shown like that. Why is the force normal? Do you have a question, Becky? No, okay. Why is the force normal shown going down? Okay, the person is sitting on their seat, the seat is above them, and as long as they don't fall out, they're pushing into the seat above them, and so the normal is down. What's the condition for the person to fall out? They're no longer going to be pushing into the seat, right? And so what's the force normal if they fall out? Well, it'll be 0 if they fall out. If the force normal is up, that means we glued them to the seat. Right? We could have, but we generally don't because then we want to get them out afterward. You had a question, Edika.
I was thinking the force normal was down, so the cart pushing against the metal.
Well, because I'm looking at the person, it was on the person. On the carts, it's also down because it's pushing up on the rail. Okay, so we've got a free body diagram. And I'm sure this will come back to me. Okay, it just jumped to who knows where. So we have the free body diagram there. We want to find the minimum speed. It didn't give us the radius. Oh yeah, it did. It gave us the radius as 20 meters. So now I have to go through my physics thinking. My physics thinking starts with the condition for them to fall. I'm not going to write it all out this time. But the condition for them to fall is when force normal is 0. And so I'm going to, once again, if they're going in a circle, I know they have to have an acceleration toward the center of v squared over r. And so I'm going to apply Newton's second law and then find what V corresponds with the force normal of 0. So applying Newton's second law, in what direction should I apply Newton's second law? If it's doing a circle, toward the center. So I look at my picture and look, both of those forces are pointing toward the center. So that means I have force normal plus force of gravity, plus, because they're both toward the center, is equal to mass times centripetal acceleration. Now I say minimum speed when force normal equals 0. So 0 plus, and instead of force gravity, I'll show mg equals mv squared over r. Now notice they didn't give us the mass in the problem. People who want to put numbers into problems would say, oh snap, I don't have the mass, I can't solve either side. But people who are more experienced at problem solving say, yippee skippy, because they say yippee skippy a lot, I can divide everything by mass and it cancels away. Of course, 0 divided by mass is still 0. We're all good with that, right? And so I end up with the equation that simply is v squared over r is equal to g. Therefore, v is equal to plus or minus square root of gr. Mass didn't matter. That's kind of good to know. It doesn't matter if you're big like me or small like Gila. You'll have the same situation for you to fall out of the roller coaster. As long as it's going faster than that speed, both Gila and I will be safe. It's not like, oh, Richard's heavier, he's got to have a faster speed or he falls out first. So then you just go ahead and calculate what's the square root of g times r. They gave us the radius is 20. 20 times 9.8, 196. Square root of 196. I don't know, it's more than 40, less than 50. Right?
What was it?
196.
14 point something?
Or, yeah, what am I saying? 40 and 50. Yes. It's, I was thinking one more zero on it. Okay, so yeah, I'm going to go with Corso. What'd you say, around 14?
14.3, so I don't know.
So let's just say approximately equal to 14 meters per second and move on. Now I put plus or minus because whenever you do the square root, you have two answers, plus and minus. But since I was only asked for the speed, I didn't care about the minus, I just need the magnitude. And of course, it could be going clockwise or counterclockwise, either direction you would stay on there if you're going faster than that speed. Yes. Any questions about solving that problem? What direction did I apply Newton's second law? Toward the center. Now, sometimes we're going to have to apply it more than one direction, such as in this next problem. A car is going around an unbanked curve at the recommended speed of 11 meters per second. And the question then is blah, blah, blah down here. So going around the curve, they drew one picture. I often actually draw two pictures. One picture that shows a front view and one that shows a top view. So I usually would break this up and say top view here's my car traveling with speed this direction. Well, let me put it on the other side. And I have a force of static friction between the tires and the road, pushing it in toward the center. How do I know friction is pointing in toward the center? What direction would the car slide if it didn't have any friction? It would go straight. So it would go straight down if there was no friction. But I have to have a force toward the center to keep it going in a circle. That force is going to continue changing directions always toward the center to keep it going in the circle. So oftentimes people get the directions confused because the direction it would go is straight down, but the direction we need is perpendicular to that to make it go in a circle. So there's the top view, and then I, of course, have the radius of my circle here. And then we go to the side view. So in the side view, here's my car. And then I meant to change the color. And the pen stopped on me. I'm just going to buy another pen. This is ridiculous. If I buy one today, it'll be here by the time I get back. Force of gravity is equal to mg. Force normal. Force of static friction. So I have two different pictures, one that shows the vertical, one that shows the horizontal. In the next problem, you'll see why that's more useful to have both pictures. So now that I have those, I need to read the rest of the problem. If the radius of curvature of the path is 25 meters, so that's my radius, and the coefficient of static friction between rubber and the road is 0.70, does the car skid as it goes around the curve? So now I have to think about, how do I answer that question? Does it skid? How would I know if it's going to skid or not? Okay, if the force necessary to stay in a circle is greater than the maximum force of static friction. Remember, the force of static friction is less than or equal to mu static times force normal. So I'm going to go through my problem and I'm going to calculate what force of static friction is necessary to stay on the curve. And if that is less than mu s times force normal, then it stays. If the force necessary is greater than mu s force normal, it skids off the track. So let's do this real quick. We have two directions, and I'm going to draw my coordinates. And I'm going to have y is up, and radial is toward the center of the circle. Right, so I just chose my direction for r to be toward the center of the circle, and then, of course, y is perpendicular to that. And so the sum of the forces in the y direction equals mass times acceleration in the y direction. How much is the car accelerating in the y direction if it goes around a flat curve? 0. That's the kind of thing that the problems don't tell you. They want you to, once again, use your critical reasoning skills to say, okay, its vertical velocity is constant at 0, hence the acceleration is 0. Then I look at my picture in the y direction. I have up is force normal, down is mg. So the force normal is equal to mg. Not always the case. The next problem, that will not be true. So that was in the y direction. Now sum of the forces in the radial direction is equal to mass times acceleration in the radial direction, which is mass times v squared over r. Look at my picture. What do I have in the radial direction? I have the force of static friction. Ashley said it, just soft enough that no one here. So that force of static friction that's necessary to go in a circle is equal to mv squared over r. And then for my test, I know the force of static friction is less than or equal to force normal times mu static. So that's going to be 0.70 times mg. The speed was 11 meters per second. And the radius was 25 meters. So 11 squared, 121 divided by 25, just under 4.5. Well, what is 11 squared divided by 25? Someone with the calculator?
12.84.
12?
4.84. The whole.
4.84.
Not just the.
What was the question?
Okay, it was 11 squared divided by 25, or 121 divided by 25. It surely seems...
4.84, yeah.
Okay, 4.84. Wow, my half was wrong. And the units there are going to be meters squared per second squared divided by meters, so meters per second squared. And down here we had mass times 0.7 times g, 0.7 times 9.8, 0.66, or it's not 0.66, 6.86. Okay, so we look at this. The maximum static friction that I can get is 6.86 meters per second squared times the mass. I don't even care what the mass of the car is, because the force of static friction I need is 4.84 meters per second squared times mass. Which one's bigger? Which one's bigger, the static friction needed or the maximum? The maximum is bigger, hence it stays on the curve. Right, so we're able to go through this, and of course, you drive on roads and it says, warning, maximum speed, 60 miles per hour. If a physicist made those signs, they would go through this calculation, take the standard coefficient of static friction between tires in the road, and calculate the maximum speed. But anyone who's driven on a freeway knows you can always go well over those maximum speeds they post for the curves. They're putting in a safety margin that often seems ridiculously large. Every now and then they really do mean those signs, though. So if you don't know a road, you should follow the signs. Just precaution there. Okay, what happens if the driver ignores the highway speed limit and travels at 18 meters per second? If you change to 18 meters per second, what changes in everything I've done? Only this. Instead of 11 squared over 25, it's 18 squared over 25. So what's 18 squared over 25?
Well,
12.96?
yeah.
What do we have then? The force necessary is 12.96 meters per second squared times mass. That's almost twice the maximum you can get from the tires. So the car goes skidding off. Now, of course, 11 to 18 doesn't seem like much, but you're, going a significant percentage higher speed. And then finally asks, what speed is safe for traveling around the curve if the road surface is wet? So mu(s) is 0.5. So now for the last part, you're coming back, what speed is safe? Well, the safe speed is when these two are equal to each other. That's the maximum safe speed. And so you just go through again, you put in 0.5 mg, and you see that the 11 meters per second squared rounded off to integers, 4.84 is pretty close to 4.9 that you would have as the maximum. So that's where the 11 would come from. It would be the maximum when it's wet, if it was actually done by a physicist who assumes that you're going to be a perfectly safe driver. Okay, now a question before I do my next problem. This is a clicker question, y'all. What is the purpose of a banked curve on a highway? Okay, I'll give it about 10 more seconds here and we'll go. Okay, everyone's answered. I'll stop now then. We had 5 who said to increase the normal force, 15 who said to increase the force of friction, 3 that said to look cool, 1 that said, 3 that said to normal force as horizontal, 1 said to look cool, 0 that said to save on construction costs, and the last number doesn't show up on my screen. Let's see, that's 24, and we had 29, so 5 for the last one. Okay, so we had a lot of variation on why they banked them. The majority answer was to increase the force of friction. I'm not going to ask somebody to explain it this time. We're going to go to a problem to look at what happens with the banked curve. So here's the banked curve. Car on this banked curve is moving away and turning to the left. And what we want to do is find the maximum speed before it slides, all in terms of variables. No numbers here, just in terms of variables. So if I'm going to find the maximum speed before it slides, how do I start the problem? What's the first step? Okay, draw a diagram and get a Freebody diagram. So once again, just like before, I'm going to make 2 diagrams. One that's a top view. Force of static friction there. So there's my top view, and of course I have the radius r. And then I go to a side view. And the side view is a little more complicated now because I have a triangle. I've got to do a better job. Like I said, got to do a better job. That's a better job. Some angle of elevation theta. And then I have my car on here. And what direction are the forces on the car now? Start naming forces and the direction each one points. Okay, gravity straight down. Okay, normal is perpendicular to my incline, right? So normal is like that. We're very clear that normal is not vertical. Okay, what else do we have? Force of static friction. What direction is that going to point? Okay, I have multiple answers on this. And a good teacher is going to point out, it depends on the speed. If the car is stationary, what direction would it naturally slide? Downward. And so the force of static friction would be upward if the car is going slow. If it's going fast, then it would naturally slide up the track. And so what direction is the force of static friction going to be? Down. Right, so we were looking for the maximum speed before it slid. So since we're looking for the maximum speed, we'll have the force of static friction go like this. Now we can look at this right away and see 2 things. Number 1 is the static friction component that's toward the center is not all of the static friction anymore. It's only part of it. And the force normal now has a component toward the center. So if we look back at our quiz question, we had to increase the force of friction. So if it's going around the corner, force of gravity is down, force normal is not parallel to force of gravity, but the force normal is going to have some component that's toward the center, some component that's vertical. the vertical component of the force normal is going to have to balance the force of gravity. So I can look at this and I can say my two directions I'm going to choose are horizontal and vertical. Is that what you expected? I assume the answer to be no. Because what did we do on inclined planes previous to today? Like when I had the skier, we made one direction parallel to the slope and one direction normal to the slope. Now I went to vertical and horizontal again. And the obvious question is, why did I do a dorky move like that? The answer is, what direction is the acceleration of the car? It's horizontal. And so I chose my coordinate direction. So one coordinate was in the direction of the acceleration, and the other coordinate's perpendicular to that. So that's why I chose them that way. Now, if I do the sum of the forces in the x and y, or r, so I'll put the r direction here, and the y direction here, I'll break them into components. So my force normal, my force gravity, seriously, move. My force of static friction. And when I look at my coordinates, only one of these is already resolved. Which one is already all in the x or y direction, or r or y direction? Gravity. Gravity is all in the y direction, so it's 0 in the x direction. It's down, so minus mg in the y direction. Force normal. How do I break that into its components? Identify this as the angle theta. And the radial part is the opposite side. Is that positive or negative for the radial part? It's positive. It's positive because it's the same direction as that arrow. You have to make sure you look at your coordinate direction definitions.
You can't define it the other way and call it negative.
I could define it the other way, but then I'd have my acceleration is also in the negative direction. So yes, I could. So it's going to be positive force normal. That's the opposite side of the triangle, so sine theta in the x direction. How big is force normal? I do not know. I put force normal without a vector sign. That means the magnitude of force normal. It's an unknown. What about in the vertical direction? Is it going up or down? The force normal. Up. So that means it's positive. This is the adjacent side. So there I have my force normal broken into components. Remember, it is important for you to be able to identify that this top angle is theta, not the bottom angle is theta. So make sure you have a way in your head. I went through it before. My easy way is, if it was horizontal, which angle would be 0, and then which one grows as it moves up. But have a way to identify so you know which angle is which. And I drew these lines for the components parallel to the directions I had identified. As I said, I made mistakes like that when I was in college. Now the force of static friction. I need to break the static friction into components as well. So there's one component direction, there's the other. Which angle is theta for that triangle? It's this one here, because it's the angle between, this was horizontal and the slope. That's the angle between horizontal and the slope. So that was actually easier to identify. And so, go ahead.
What were you saying about the angle we should use?
The angle, okay, so let me draw bigger. Here's my force of static friction. And so, which angle, this one or this one, was the angle of my incline? And it was this angle because the angle theta was between horizontal and the slope. This is between horizontal and the slope. And so that means my radial component is the adjacent side. And then the vertical part is downward. So there I've broken each of my forces up into its components. Now technically the force of static friction is less than or equal to that, but I'm looking for the limit. And so since I'm looking for the limit, I'm going to change that less than or equal to an equal sign. I have the x or the radial and the y direction. I now will apply my Newton's second law in both directions. Why? Because I have two unknowns, the speed v and the force normal. So I need to solve for both of those, and thus I need two equations. So let's do first the sum of the forces in the y direction is equal to mass times acceleration in the y direction. If it's doing a flat circle, its vertical velocity is constant at 0. And so the acceleration in the y direction is 0, which makes my life easy. So I can solve this for force normal. So I move the mg to the other side of the equal sign and factor out the force normal. Divide by and there I have my force normal. Now I come over to the radial direction. Since it's going in a circle, that's mass times v squared over r. And so now I take my y components and add them up, Newton's second law. I'm trying to solve for v, so I substitute in force normal. First, I'm going to substitute in force normal. Or not substitute in. I'm going to solve for v squared. Now I substitute in the force normal. Come on. And my masses will cancel. And I'm left with v squared is equal to rg sine theta plus mu s cosine theta over cosine theta minus mu s sine theta. Now that was some more complicated math than we've been doing. I had to solve the two equations, but I found an equation for the speed as a function of angle. That's the maximum speed I can go for different angles and for the coefficient of static friction. Assuming, of course, I made no mistakes. So there we have it. We ran out of time, so I don't get to talk to you about what causes a hurricane. And then we were going to start with work after that. So we'll pick up here on Friday.